Hello student, how are you? In my today's video, we are going to learn another mechanism, that is mechanism for Williamson synthesis of ether. So my dear student, the Williamson synthesis is an important laboratory method for preparation of both symmetrical as well as unsymmetrical ether. Alright, so what is the chemical equation for this? Chemical equation. So in this reaction, one alkyl halide is allowed to react with sodium alkoxide. See, this is alkyl halide, and this is sodium alkoxide. Okay. So when alkyl halide is allowed to react with sodium alkoxide, it will give ether. Now, to differentiate these two R, let me write this is R dash, then I will mark this as the R dash. R and R dash may be same, may be different, because by this method we can prepare both symmetrical and unsymmetrical ether. Alright? Here you see what is the byproduct? NaX. This X will be substituted by RO. Here it will be X minus Na plus. So Na plus X minus NaX. Then this is ether. Now we will learn the mechanism for this particular reaction. But before writing the mechanism, you see, as I said, by this method we can prepare both symmetrical and unsymmetrical. Let us see an example. Suppose if we need to prepare an symmetrical ether, suppose methoxymethyl. This is symmetrical ether because both alkyl groups are similar. That is methyl group. This is methoxymethyl. For that, I have to take alkyl halide, so methyl bromide, and sodium alkoxide, that is sodium methoxide. If I take sodium alkoxide, that is sodium methoxide, and methyl bromide, then what ether will get? Methoxymethyl. Byproduct is obviously sodium bromide. Now, if I change this alkyl group, suppose this C2H5, then it will be C2H5. That time it will be an unsymmetrical ether because alkyl groups will be different. Alright? Okay. Now, let us see the reaction mechanism. So, reaction mechanism. So mechanism for this reaction, my dear student, this is SN2 mechanism. What? SN2. That is nucleophilic substitution bimolecular. So in this reaction, sodium alkoxide acts as nucleophile. Let me write the general reaction, that is sodium alkoxide. This is nucleophile, and alkyl halide, that is you write RS, alkyl halide acts as substrate. Okay. Now as we know, in nucleophilic substitution reaction, the nucleophile attacked on the carbon to which halogen is attached. Alright? This carbon halogen bond will break. So bond breaking will take place between carbon and halogen. At the same time, bond formation take place between this oxygen and carbon. Alright? So as a result, we will get ether. This is ether. Byproduct is NaX. This is ether. So this is a nucleophilic substitution by molecular reaction. In transition state, two molecules will be involved. Already we have learned SN2 mechanism. So we won't discuss in details, but you remember Williamson synthesis always carried out by SN2 mechanism, SN2 path. So my dear student, one very important aspects of this particular reaction now we'll discuss. That is what, for this reaction, this substrate, that is alkyl halide, must be 1 degree alkyl halide. What this is? Must be 1 degree. That is primary alkyl halide. Why it should be primary alkyl halide? Because as we know, this reaction involves SN2 mechanism, and SN2 mechanism always 1 degree alkyl halide is more reactive than 2 degree, than 3 degree. Okay? So, Williamson synthesis for the preparation of ether is most suitable for 1 degree alkyl halide. This is not favorable for 2 and 3 degree because of steric hindrance. If this 2 degree and 3 degree, this alkyl group will be bulkier group and it will have an inhibiting effect. It will inhibit the attack of nucleophile due to steric hindrance. Alright. Now my dear student, what will happen if suppose secondary or tertiary alkyl halide will be allowed to react with sodium alkoxide? Okay, if we allow secondary or tertiary alkyl halide to react with sodium alkoxide, then elimination competes over substitution. Means we will be getting the eliminated product, that is alkene. For example, let me show you. In place of R, if I take suppose tertiary, this third butyl group, this is a 3 degree alkyl halide. This is suppose this is 3 degree group, 3 degree alkyl group. So alkyl halide will be 3 degree alkyl halide, tertiary butyl bromide. This is a 3 degree alkyl halide. Alright. Let us take suppose CH3O sodium alkoxide. Let us take this is. Now what will happen? Since this group is big, is sterically more hindered, so what will happen? Here substitution will not take place. Here elimination will take place. How elimination will take place? Let me show you. Student, when 3 degree alkyl halide is treated with sodium methoxide, then what will happen? Let us see. If we write this as CH2H, then this time is sodium methoxide will better act as base rather than nucleophile. So it will abstract a proton from here. It will abstract a proton. This electron will transfer, this electron pair will transfer here and will form a double bond here. CH3, C, double bond, CH2, here it is, CH3. At the same time, this bromine will leave, otherwise what will happen? Carbon valency will be 5. So it is Br minus Na plus, we will be getting NaBr. Now since methoxide group will take up, will abstract a proton. When this electron pair will come here to form a double bond, this will leave as a proton. So H plus will come and join with oxygen. Then what will form another product? That is CH3 OH. So what I mean to say, if secondary and tertiary alkali halide are treated with alkoxide, substitution reaction does not take place. Okay? Here elimination competes over substitution. This is the eliminated product. That is, you see what is the name of the product? 1, 2, 3. We are getting alkene. 2-methyl propene. This is 2-methyl propene. We are getting an alkene. This is a elimination reactions. Okay, my dear students? Have you understood? So what we have learned today? Williamson synthesis. What are the reactants? Reactants are alkyl halide, but alkyl halide must be primary alkyl halide. Alkyl halides are treated with sodium alkoxide to give ether, and ethers we can prepare both symmetrical and unsymmetrical ether. That is one advantage. Okay, and it must be primary, cannot be secondary and tertiary, because secondary and tertiary alkyl halides have more steric hindrance, inhibiting effect. If we treat secondary and tertiary, elimination competes over substitution. We will get eliminated product, mostly alkene. Have you understood, students? Okay, thank you.